So today we're going to start chapter 10, section 1. We're going to learn about lines and segments that intersect circles. So what you're going to see today are a lot of vocabulary terms. So let's first define what a circle is. So a circle is the set of all points in a plane that are equidistant from a given point in that plane. That given point is called the center. A radius is going to be a center a segment whose endpoints are the center and then any point on the circle. The plural of radius is called radii. So I'm going to go ahead and draw a picture of a circle, and I'm going to label that for you. So let me go ahead and draw my circle here. When you name a circle, you have to either write the word circle and then the center point. So I can name this circle that I just drew, circle M. Or just like before when we saw triangles, remember you could just draw a picture of a triangle instead of writing the word triangle. So the same thing's going to apply for a circle. You can draw a little picture of a circle, put a center point in it, and then put the capital letter that represents the circle center. So when you name a circle, you either need to write out the word or draw a picture of a circle. Now the other vocabulary term that we saw on this slide was the vocabulary term radius. So a radius goes from the center point to any point on the edge. The radius is always usually indicated by a lowercase letter r. And it doesn't matter where a radii is drawn, it will always have the same measurement. So if I told you that this radius that I just drew in here has a length of 3, then any other radii that I draw in here, whether I draw one up this way from the center to the edge, it will also have the same length, and it'll have a length of 3. I could draw another one anywhere from the center to the edge, and it will always be the same size as all the other radii in the picture. It goes from the center to the edge of the circle. So the next one has the vocabulary terms chord, diameter, secant, tangent, and point of tangency. So a chord is a segment whose endpoints are on a circle. Now, the radius that we saw on the previous slide, this is also a segment. So chords, radiuses, or radii, and diameters are all chords. So a chord is a segment whose endpoints are on a circle. So what it does, it's a segment that goes from one edge of the circle to the other edge. So it goes straight across. The diameter is actually a chord, but it's a special chord because it must contain the center of the circle. Then a secant is a line that intersects the circle in 2 points. A tangent is also a line in a plane of a circle that intersects the circle in exactly 1 point. And that point where it hits the circle is called the point of tangency. So now I'm going to draw a circle, and I'm going to add in all of these parts into the circle. So I'll draw my circle first. I can add in my center point, and it doesn't matter. It's always just a capital letter. I could call this circle C, and then if I wanted to draw a chord, I'll go ahead and draw the chord in blue. The chord is a segment that goes from edge to edge. And you can draw chords all over the place, but it just goes from one side of the circle to the other. Now, when that chord goes through the center of the circle, then that chord turns into a diameter. So it goes through the center, but it goes from edge to edge. I could also draw a diameter up this way. Doesn't really matter. It just goes from edge to edge, but it goes through that center point. So the red ones are diameters. And the blue one that I just drew is an example of a chord. However, technically, diameters are also chords. Next, I'm going to draw in a secant. And the secant is a line that hits the circle in 2 points. So a secant, I could draw it this way. And notice it hits the circle here and here. And a secant is a line. Now we're also going to see secant segments. This is where we're going to be referring back to chapter 1, where we learned how to name lines and segments. And you're going to need to pay attention to the picture that's on top of the capital letters. But we're going to see that coming up. Then the last one that we need to label is the tangent. And let me go ahead and label that one in gold. And the tangent is a line that only touches the circle in 1 point. So it would skim along, and that point where it touches the circle is called the point of tangency. So the gold line is a tangent line. Now the next slide actually has another circle with all of this labeled as well. But again, the more practice you get of identifying these parts, the easier it makes some of the problems. So here is the same vocabulary terms we just saw. So the chord, remember, goes from edge to edge. The diameter, remember, needs to go through the center point. So it needs to be a chord that goes through the center. This would be your diameter. And then the secant, remember, it goes through the circle and it hits it in 2 points. And it's a line. So it's hitting it here on this edge and over here. And then remember the tangent, it's just grazing the circle, or it's just skimming along the bottom of the circle. So the tangent skims along and it hits it at 1 point, and that point is called the point of tangency. Okay, so now they want us to name all of these parts of each figure. So what we need to pay attention to is it a segment or is it a line? So here they're telling us that point O is the center of the circle. So if I go ahead and find OM in my picture, OM is this segment right here. Notice it goes from the center to the edge, making OM a radius. Then MN, that's this segment right here. And notice the picture of the line on top, making this a segment, and this is called a chord. Now, they've changed the picture on top of the MN. So if this were to extend out and turn into a line, then now, because of the picture on the line on top, this is now a secant. But when it's got the picture of the segment on top, then it's just a chord. It stops. MQ, this is a segment that is going through the center, and it's going from edge to edge. So here, MQ, technically this is a chord, but the better name is diameter. If on the test you told me it was a chord, I would give you credit. But the better name is diameter because it goes through the center point. Next, it's asking us to identify ML. ML is over here, And notice the picture on top is a segment. So generally when it's outside of the circle and it touches the circle at one point, this is a tangent. But because the picture on top of the M and the L is a segment, this is actually a tangent segment. And if you notice, the next question has the line on top. So as soon as they change the picture, then you're just going to call it a tangent. Because by definition, a tangent is a line. But if they give you a picture of a segment on top of the capital letters, then you name it as a tangent segment. And then point M, that is where that tangent is touching the circle. So point M is your point of tangency. And coming up, we're going to learn a theorem about tangent segments. So this is why it's going to be important that we understand that a tangent can be a segment. There are also secant segments, but for right now, what we're worried about is all we can see in this picture is a tangent segment. The next one is talking about common internal versus common external tangent lines. So in order to determine if a tangent line is internal or external, what they want us to do is draw a line or a segment that connects the centers of the circles. So let me go ahead and draw the centers in each of my circles. And now I'm going to draw a segment that connects those centers. This pink line is going to help me to determine, is my tangent that's drawn internal or external? So in the circles that are on the left, this blue line here is a tangent line to both the little circle and the big circle. So this tangent line is in common to both the little circle and the big circle. But because that tangent line does not intersect the pink line, this is considered a common tangent, but more specifically, a common internal tangent line. I'm sorry, external. Sorry, it's not inside, it's external. Common external tangent. Now, you're going to be doing things like this in the homework tonight, and they're going to ask you to count how many tangents it has and how many are common internal or external. This is where I want you to draw them. Now, these two circles actually have one other common external tangent, and you can skim it along the bottom as well. So the other common external tangent would be skimming along the bottom. And we can tell that it's external because it does not intersect the pink line. Now, for the other figures, on the one on the right, this is the tangent line. It's in common to both circles, but notice it intersects that connecting pink line, making this red line the common internal tangent. Now I can draw another one the other way. So I could also draw and have it skim along this way. And this would also be another common internal tangent. So both of these would be common internal because they intersect that pink line that connects the centers. So when the circles are sitting side by side, there's actually 4 common tangents that you can draw. 2 are external, 2 are internal. Now, you may have 2 circles sitting side by side, for example, let's say I have a little circle here, and then a larger one over here. And let's say you have a line that's drawn, and let's say it's going to skim along the little one, but then it goes into the bigger one. So for the little one, this line is tangent because it hits it once, but for the bigger circle, this is a secant because it hits it twice. So again, just because the circles are sitting side by side doesn't necessarily mean that when a line is drawn, it's going to be tangent to both. It could be a tangent and a secant. Doesn't necessarily have to be tangent to both if it goes through the other circle and hits the sides twice. We're going to define congruent and concentric circles. So congruent circles are just circles that have congruent radii. So for example, I could have two circles that are just sitting side by side. And as long as they're both labeled with a radius of the same length, you can say that these two circles are congruent. I could call this circle B and this circle C, and I could say that circle B is congruent to circle C because they have the same radius length. So that's what we're looking for when we want to describe congruent circles. We're looking for two circles that have the same radius length. Now, it doesn't necessarily have to be two separate circles. It could be a circle within a circle, like not necessarily like the picture that's there, but for example, let's say I have this circle, and then let's say I put another circle inside it, and it's not necessarily concentric, but it's going to have the same radius length. So let's say I told you this radius was 3, and then the blue one also had a radius of 3. These would be congruent circles. It's sort of I'm trying to draw it 3D, but just know that those circles would be congruent if they have the same radius length. Now, the other vocabulary term that's on this slide is concentric circles. And concentric circles, a real life example could be like a dartboard or a bullseye. So they're circles within a circle. They're all going to have the same center, but they're going to have different radius lengths. So for example, let's say this inner circle, let's say this radius length is 2, but then the outer circle still has the same center. Its radius length could be 4. So there's circles within circles, and they're not going to have the same radius length. I could even have another littler one right here. And they would all have different radii length, making them concentric if they share the same center. Next is tangent circles. And these are coplanar circles that are tangent to the same line at the same point. So this one sort of looks like a snowman, but the line that's tangent to both is squeezing in between, and then the point of tangency is the same for both. Over here, the picture on the right here, these are not concentric circles because they don't have the same center, but they do share the same tangent line, and the point of tangency would be right there. So when the line is tangent to both circles that are in the same plane, then those would be considered tangent circles. All right, so Theorem 10.1, again, don't memorize the number. It actually has a name, and this one is called the tangent line to a circle theorem. And what this states that in a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at the point of tangency. So in my picture here, B is my point of tangency. And notice, in order for BC to be a tangent line, I would have to see a right angle here indicating that AB is perpendicular to BC, or they'll be giving it to you like it's written here. What we're going to be doing with this theorem is we're going to bring back chapter 9, and we're going to be doing Pythagorean theorem and special right triangles, 30, 60, 90, and 45, 45, 90s. Because what we can do is I can connect A to C, and now I've just formed a little right triangle here. And in order to find, say, the length of the radius, or the length of BC, or AC, this is where I can use my knowledge of right triangles. So theorem 10.2, again, don't memorize the number, it's got a name. And this theorem is called the external tangent congruence theorem. So external tangent congruence, and you could just put the symbol for congruence if you don't want to spell out the word, congruence theorem. So you could abbreviate and just put the symbol there. And what this one states is that tangent segments from a common external point are congruent. So my tangent segments in this picture are AB and BC, and their common external point is B. So because these tangent segments are coming from a common external point, AB is congruent to BC. You can add a little congruency symbol on top. So AB is congruent to BC. Sort of looks like an ice cream cone or a snow cone. All right, so example 2 actually has 2 parts. So I'm going to actually label my picture for part A in red. Now also what I'm going to give you is the fact that OT is tangent to circle R. So because I'm told that OT is tangent, that tells me that this right here is perpendicular, so I have a little right angle there. So now I'm going to label OR as 6, OT is 8. In order to find the length of RT, I'm going to need to use Pythagorean theorem, because I know that when a line is tangent to a circle, it will be perpendicular to the radius at the point of tangency. So what I'm going to do here is, if you recognize that this is actually a Pythagorean triple, it's actually the 6, 8, 10, a scaled up 3, 4, 5, then you don't have to do Pythagorean theorem. However, if you didn't recognize that, what we're going to use is a squared plus b squared equals c squared. I could label either leg as a or b, it doesn't matter, because what I'm looking for is that hypotenuse, which is my c. So 6 squared plus 8 squared equals c squared. 36 plus 64. I get 100 when I add them. And now I need to square root it. Now, what we saw in our little algebra review, now technically when you use this square root method, you should be getting both positive and negative 10. But we don't want a negative hypotenuse. So the only answer we're going to keep is the positive 10. So the length of RT is 10. Again, if you recognize this 6, 8, 10, it is a common Pythagorean triple. And then you wouldn't have had to have done the Pythagorean theorem if you recognize this. Now, part B, now the information that I just labeled in red is now changing. I'm now going to label it in blue. So everything that I wrote on this triangle in red doesn't apply now, or the 10. Now I'm going to do part B in blue. So I'm going to label angle OTR as 45 and side length OT as 4. So now if you recognize, this triangle has now turned into a special right of 45, 45. So if you wanted to pull it out so you can see it a little bit better, OT is 4, and this angle's 45, and so is this. And if you remember, the two sides that are forming the right angle, these two legs, are always congruent. And then the hypotenuse is whatever A is, and these are both A's, is A square root 2. So to find the length of RT, all I do is take 4 and put square root 2. So this is where what you just took a test on in chapter 9 is going to come back in this chapter when we start creating these triangles with our tangents. Now, one other thing you could have also done is, let's say you forgot the relationship of the sides of the 45, 45. You can also do Pythagorean theorem as long as you realize that the two legs, OR and OT, are both 4s. And then to get RT, just do Pythagorean theorem, square the 4s, add them. Now you have to square root this, and then C is equal to the square root of 32, but we need to leave it in simplest radical form. So we'll do a factor tree. And then this turns into 4 square root 2, the same answer I got when I used my knowledge of special right triangles. So when the angles are given to you and it's a 45, 45, 90, or 30, 60, 90, you can also use your knowledge of special right triangles instead of doing Pythagorean theorem. Example 3, it wants us to name a line tangent to circle P, the little circle, but not to the larger circle O. So I can see that circle P has a tangent line right here because it's hitting at the point of tangency of B. However, if I keep extending this line and keep making it a line, notice it turns into a secant for circle O. So something that's only tangent to P would be line BO, or you could name it as OB. Now, in order to name a common external tangent or a common internal tangent, I need to draw that segment that connects the centers. So we have circle O and circle P. So here's my imaginary line that connects the centers. So to find a common external tangent to O and P, external could be this one down here at the bottom, CD, would be a common external because it does not cross that pink line. So a common external tangent could be line CD, or in reverse, DC. And then the common internal, where it is going to intersect that pink line, would be tangent AE. Or in reverse, EA. Because remember, the common internal tangent has to intersect that segment that connects the centers. Example 4. So it says circle M and N are tangent at point P. PR and SR are tangents to circle N. Circle N has a diameter of 16. And then it's giving us the length of PQ. It's 3. And RQ, it's 12. So this one's 3. This is 12. It also told me that PR here and SR are both tangents. These are tangent segments. And I learned that external tangent to a circle theorem that states that these two tangents are going to be congruent. So if PR, I can add 3 plus 12, PR is 15, so is RS. So I've already answered 2 of the questions just by labeling my picture. I've answered C and D here because those 2 tangent segments are congruent. And now let me go back and label my diameter. That was the other thing that was given to me. That circle N has a diameter of 16. So I'm going to draw a diameter in here. And it's 16. Now, for part A, it wants me to find PM. Well, PM is this little segment here, the radius of circle M. So if you recognize that the radius of circle N, the big circle, is actually the diameter of the little circle. So if the radius here of the big circle is half of 16, which is 8, and then to turn that into a radius of the little circle, then the radius of M is 4. So that's the answer to PM. It's the radius of the little circle. Now, for MQ, since point P is a point of tangency, I know that there is, at the end of this radius, a right angle. So MQ is actually the hypotenuse of that right triangle. So I'm going to pull this little gold triangle out. And I already know that this side is 4 and this side is 3. So if this is 4 and this is 3, to find the hypotenuse, common triple. If you didn't recognize that this is a 3, 4, 5, then what you need to do is this could be A, this could be B, and we're looking for C, which is MQ. So I can do A squared plus B squared equals C squared, and C squared is the MQ. So 3 squared plus 4 squared equals C squared. 9 plus 16, 25. Square root it, and I get C is equal to 5, which is what I was asked to find in part B, which was MQ. So this little piece right here is a 5, and that's MQ. Now they want me to find NS. Well, if you recognize NS over here, that's a radius of the big circle. And I already found that. That was 8. So NS is 8. Now to find NR, I'm going to have to draw and make another triangle again. So NR is right here. And again, point S is a point of tangency. So I got a right triangle here. So if I pull this one out, S, R, and N. This I already found to be 8. This I already found to be 15. I'm looking for the hypotenuse. This is also another triple. So if you recognize the 8, 15, 17 triangle, then you don't have to do the work. However, a squared plus b squared equals c squared. The 8 could be a, the 15 could be b. So 8 squared plus 15 squared equals c squared. 64 plus 225 equals c squared. Add it, I get 289. Square root it, and I get 17. So NR, the last question, is 17. So again, once you see that you have tangents, and if it's intersecting the radius, then we know we've got perpendicular, and then we're gonna form right triangles. And we're either gonna do our special right triangles or Pythagorean theorem. So that is it for 10.1. Now, tomorrow, I'm going to do some additional examples to help you with the homework for tomorrow night. And you're gonna be foiling and factoring in the notes tomorrow and in the homework tomorrow night.